Okay, so back after a little bit of a break, and today we'll talk about 5 problems I've chosen for this week, and it's not really any particular theme, I guess, just building on some of the things we've done before, and also maybe try to get back to it a bit. Okay, so the first problem is called try, and basically, if you read the problem, they give you 3 numbers that are relatively small. It could be any number from less than 100. One thing that you have to be careful, although in this case it probably doesn't matter too much, is that it just says that there's 3 integers less than 100, but it doesn't really say anything about the numbers being positive here, although it says it here. Okay, so you have to be careful. Do you have to worry about negative numbers and 0? In this case, you don't have to worry about any of that. Why do we have to worry about 0? Because you want to try the 4 operations: add, subtract, multiply, and divide. And if 0 is ever a possibility, then you have to worry about divide by 0. So anyway, the point is that it's not a possibility, so you don't have to worry about it, which is good, but we always want to read it, the problem carefully, and make sure that we don't have to worry about all these little tricks. All right, so what you're supposed to do is to output a single line output a valid equation containing 3 integers in the same order and equal signs in one of the 4 operations. If there are multiple solutions, output any of them. And the equal sign can either be between the first and second one or between the second and third one. So basically, you just have to try everything, right? So you have A, B, and C. So basically, you can either have equals to, plus, minus, times, and divide here, or it could be plus, minus, times, divide here, and then equal sign here. And so there are basically 4 choices here, 4 choices here. You try 8 different things. One of them is guaranteed, at least one of them is guaranteed to work. So you just try them all. The only issue, I guess, is to see how you write the code properly so it's not too messy. The other thing is you have to make sure that when you check for division, okay, so if you want to check for division, you do not write something like this. Why? Because if this is, let's say, 2, and this is, I don't know, 10 and 2, 10 divided by, sorry, not 2, 10 divided by 4, that's what I was trying to write. 10 divided by 4 will be the same as 2 because this is an integer division. So when you check for division, that A is really the same as B divided by C, you have 2 ways you can choose. You can check this. You can check that this is true and there's no remainder. That's one way. That makes sure that it's really truly divisible and B divided by C is really A. Or an actually easier way is to not use division at all and just write C times A, it's equals to B, cross multiply. This will only works if B is divisible by C and it's exactly A. So the second option is easier to write, but both options are okay. The most important thing is that you have to realize that you could have an integer division problem, so you make sure that you check for that, whichever way you feel comfortable. Other than that, I guess it's just how you structure this code. So I just basically write a function that checks if, let's say, one thing is equals to the other 2 things with some operation, and then I call this function twice with different order of arguments, right? So one would be A with B and C, and the other one would be C with A and B, to see if I can combine the 2 arguments to form the third one. And that's, I guess that's it. So let me just show you my code. So here it is. I wrote a check function Okay, so here's my code. I wrote a check function, takes A, B, and C and an operation. An operation is just going to be 0, 1, 2, 3. 1 would be 0 would be plus, minus, times, and divide. But divide, I actually check it by cross multiply. Okay. Then this checks if the first two arguments can be combined with an operation to give you the third one. Okay, so if it's a plus, then I check if A plus B is the same as C. If it's a minus, I do this, A minus B is equal to C, and so on. And again, the only real trick is the division. Instead of saying if A slash B is equal to C, I cross multiply and say it's B times C equals A. And then here, in the main, I just read in the 3 integers, and I have a string that have the 4 letters, the 4 characters that represent the symbols of the operation in the same order that I represented up there. And the reason is that later on I can easily print, right? So I can try all the operations. If A, B gives me C with operation I, then I just print out this, right? So A op bracket I, that would give me the right operation, and then B equals C. And then I tried the other way, combine B and C to give me A. And if that works, then I say A equals to B op I C. In either case, if it works, then I return 0, so I quit the main program because I'm done. And I know that at least one of them will work. So the first one that works will exit. So that's how I wrote this. If you read the check function here, I have 4 cases. Each case I return the true and false value. So there's actually no need for me to have a return false here because I know that I'm not supposed to put in anything other than 0, 1, 2, 3. But if some strange reason there's a bug and I accidentally passed something other than 0, 1, 2, 3 into op, then I just want to return false, so I can make assert false to crash the program. Doesn't matter. The point is that I have sort of a catch safety check just in case. All right, so this is the first problem. Try simplicity. All right, so maybe we read this a little bit longer than usual. For a string of letters, we define the simplicity of the string to be the number of distinct letters in the string. For example, the string has simplicity 6 because every single letter in these 6 letters are unique. And the string letter has simplicity 4 because you have L, E, T, and R. You like strings which have simplicity either 1 or 2. Your friend has given you a string and you want to turn it into a string that you like. You have a magic eraser which will delete 1 letter from any string. Compute a minimum number of letters you must erase in order to turn the string into a string with simplicity at most 2. You have 1 single string. Input will consist of a line contains with a single string with at least 1 and at most 100 lowercase letters. Okay, so basically the point is that given whatever strings you want, okay, I don't know. I'm just making something up. You want to erase letters until you have at most 2 different characters. Or in other words, another way to say it is you want to keep as much as possible so that the remaining string has at most 2 letters. Okay, so maybe we make the problem a little bit simpler. I don't know if it's simpler. So instead of at most 2, simplicity at most 2, we want to know, can we do it for simplicity at most 1? Okay, we cannot do simplicity at most 0 because if it's 0, that means we have to erase the whole string. There's no real difficulty there. If you want to remove everything except that there's 1 unique letter, that means you have to erase everything except 1 letter. So you can remove everything but A, or you can remove everything but B, and so on. So how do we remove as few things as possible? The idea is that you want to keep the most frequent letter, right? So you basically go, you have 26 different letters A to Z. You count which ones are the biggest ones. Yeah, the one that occurs most often. That's the one that you keep, the rest you throw away. So you basically look at the maximum frequency, whatever that is, and subtract it from the length of the string, because that's what you have to remove. And that's your answer. Well, generalizing this to keep the simplicity at most two, what you do is you keep the two most frequent letters. So you've just figured out the letters, the frequencies, pick the two best ones. If they're ties, don't worry about it. Just pick the two best ones, and then the rest you throw away. So in this case, A occurs twice, X occurs twice, Y occurs 4 times, B occurs 3 times, and if I haven't made any mistakes, the other ones all occur less than 3 times. So these are the two most frequently occurring ones, so the total is 7. So the number of things you want to remove is the length of the string minus 7. So length minus the max 2 frequencies. And that's basically what you have to do. But there's some special case you have to worry about. If your string started with only one letter, just a bunch of A's, then depending on how you code this up and ask for the two most frequent letters, your program may do some strange things because there is only one most frequent letters. So you have to take care of this case. But the point is that in this case, the answer is 0, right? You don't have to remove anything. So as long as you take care of this, I guess, corner case, it should not be too bad. There are many ways you can write this. And then once again, the question is, how would you write it, quickly and cleanly? So I want to show you how I write this. And you may know that I generally write things using STL as much as I can to avoid writing my own code. So here it is. Okay, it's very short. Now, what exactly do I do? First, I read in a string. Then I have an array to store the frequency of the characters. Now, why do I make it 256 instead of 26? We know that it's between A and Z, so there are only 26 letters. I'm not even going to convert the character A to Z to 0 to 25. I'm just going to use the ASCII value of the character, which is somewhere between 0 and 128. Actually, 0 and 127. The extended ASCII is between 0 and 256. So I just be safe and use 256. Most of them will not be used at all, and only 26 entries will be used. So what I do, I take all the characters in the string and I just increment the corresponding entry in the frequency array. You may get a warning, a compiler warning that says you're using a character to index into array. That may not be safe. And it's true that may not be safe because in C++, characters can be negative, can have a negative value, and then you can get strange results. But for standard characters that are in the normal ASCII range, it's guaranteed to be between 0 and 127. So as long as you don't use some special characters that go into extended ASCII range, this is safe. But anyway, if you don't like it, you can convert it to 0 to 25 by using C minus the character A. This is the ASCII value of the lowercase a, and C minus lowercase a will give you 0 to 25, provided that C, it's a letter A to Z. All right, so now I want to get the two biggest one. well, actually, I don't really care about the two biggest one. I'm not going to write some special loop to figure out the two biggest one. There is an easy function to get the maximum, but the second maximum is not so easy. So I'm just going to sort them all. So I'm just going to sort the frequencies between the range A to Z. And remember that in C++, this end of the range is 1 past the end. That's why I have to add 1 so that it actually will sort all of the A to Z, including Z. And then instead of saying, the maximum length minus the biggest 2, what I'm going to do instead is I say, okay, now that I have my 0 to 25, A to Z, but let's say, okay, A to Z, it's sorted. Where are the two biggest ones? The two biggest ones are here. These are the two biggest ones. The rest I need to delete. Now, it could be that some of these things are zeros. It might be that a lot of these are zeros, but that's okay. If there's a 0 here, just delete it. And so what I'm going to do is I'm just going to say, what is the sum of all the entries here? And that's the number of characters I have to remove. And so I start from frequency plus A, which is here. Frequency plus Z plus 1 minus 2. This is frequency plus Z minus frequency plus Z plus 1. Minus 2 would be right here. So this would be the end. And this would be exactly the range that I'm looking for. So I'm just making use of STL to easily get me everything except the last 2. And this actually will work even if you have all just 1 letters, or maybe you have 1 letter, or maybe you have only 2 letters, like this. Because in this case, in the case that everything is just A or B, then all of these would be zeros. You don't have to remove anything. And then in the case that all of the characters are the same, then this will also be 0, but you don't really care, because the important thing is that this part is 0, and you just decide based on that, you don't have to remove anything. So it all works out. The main thing is really to, once you write this code, to check that all the corner cases still works out. Okay, so that's the second problem in this set. Now what? Let's look at, I guess, the next one. Actually, let's jump to this one first. Okay, printing costs. Your workplace is starting to become concerned with the cost of toner, blah, blah, blah. And then some pages are more expensive to print than other. Your job is to write a program that helps figure out how much toner it will take. Okay. So each character requires a different amount of toner to print, and then they give you this table, right? Space, it takes 0, exclamation mark 69, and so on. Okay. And then input consists of 1,000 lines of text ending at the end of file. Each line is at most 100 characters long. For each input line, output a line giving the total amount of toner required. So basically, all you have to do is read in each line, look up this table, and for each entry in the table, add up the right amount. Right? The algorithm itself, I don't think, too hard. Okay, the problem is, how do you write this table? Are you going to, write a big if statement, a big case statement, and, it's a pain to type this whole thing in and probably easy to get it wrong. So I want to show you what I do. So the first thing I do is I'm just going to do this and copy and paste this into C++, into my source file as a giant string. Okay, so I will Where's, oh, here it is. So the first thing is I take a string and I put it in with double quotation marks around. But you realize that it doesn't quite completely work. So first of all, there's a space. So there's a space here that I didn't bother because space, it's hard to represent a space character. But since the cost is 0, it doesn't matter if we just ignore it. But then you also have special characters like double quote, because if you just put double quote in there in a string, it ends the string. That's not what you want. So you need to escape it with backslash. And there's special characters here that requires escaping. So here, single quotes, I don't think you need, but it's never wrong to escape it just in case. Definitely backslash needs to be escaped. And that's it. So in my code, I have backslash here, backslash, double backslash here, and this 3 I escaped. So I basically have a string which contains characters followed by integers, the cost. So instead of trying to hard code it with a bunch of if then else or switch statements, what I'm going to do is I'm going to parse this string by using an iString stream. So iString creates a stream object, which is kind of like cin, for example. I means input string stream, and initialize to the content of the string. So it's as if somebody's typing in the keyboard in the keyboard the content of the string. And so I just read it like this. So I keep on reading a character followed by an integer cost. And I just keep doing this. And this while loop will keep reading it until I have nothing more to read, which is the end of the string. And I use a map that maps a character to an integer cost. And that will be my table. Okay, so this is just the way I do this, just to store this table right at the beginning. And that's a compact way for me to get this cost table set up. Notice that I did not have the space character. And later on, when we actually use this table, if it tries to look up something that is not in the table, the cost is automatically 0 anyway. So that didn't bother me at all. And now I go through each line of input. So I use getLine to read one line at a time. I initialize the cost of that line to be 0. For each character in the line, I look up the cost with the cost square bracket ch, add it to the total cost, and then I print it out. So the algorithm itself is not too difficult, but what I want to show you is this sort of, I guess you can say, thinking outside the box. Copy and paste the table that they gave you, parse the string to set up the table so you don't start typing this one case at a time and probably make a mistake somewhere. Okay, so that's this one. 8 queens. All right. So this is another problem that I want to show you a little technique. Even without the technique, you can probably do it right, but the technique can make it a little bit easier. And it could be used for another problems. All right. In a game of chess, the queen is powerful piece. It can attack by any move by moving any number of spaces in current row, column, or diagonally. In the 8 queens puzzle, you have an 8x8 chessboard. Put 8 queens down, and no queen can attack each other. So they give you a board, right? Dots are space, empty squares, and stars are the queens, and you have to figure out if this is a valid solution. What do you have to check? Right? You need to make sure. So in the 8 queens puzzle, 8 queens must be placed on a standard 8x8 chessboard so that no queen can attack each other. Okay, so this is a sentence you have to make sure you understand. You have to make sure that no queen attacks each other. And the one thing that many people miss when they do this problem the first time is that they only check that no queens attack each other. And they forgot to check that there are actually 8 queens. If I give you a board that have no queens or 1 queen on it, the second part will definitely pass. And you might say that it's valid if that's the only thing you check, that no queen attack each other. If you forget to check that there are actually 8 queens, then you will fail on some tricky cases. So it's not something that it's hard to check, but you have to remember to check it. You have to be very careful when you read the problem. And then the question now is, how do you actually check, right? How do you actually check that 2 queens so that attacking each other or not? Right. So imagine that maybe you already stored a board in the 8x8 and oops. Maybe 8x8. This is 6. I need 2 more. 1, 2, 3, 4, 5, 6. So maybe you read in the board and you have stored in some way a 2-dimensional array of where the queens are, right? So maybe you have a character board 8x8 and inside it's either star or dot. Okay, and then you see a star here, maybe you see a star there, whatever. Okay, so how do you check if 2 queens are attacking each other? So one way, perhaps the obvious way that many people will try, is you just look through one row at a time to find a queen. Okay, so let's say yes, a queen. You find a queen. Every time you find a queen, you look up, you look left and right and down and then diagonal and see if you can find a queen. And if you don't find a queen, then you're good. If you find a queen, you're bad. Now, this is, I mean, you can write this, how do you go up where you have some loop that start from this, whatever the row and column is. And you just keep on decrementing row. So this is -1 and 0. So it's row and column. You subtract the row by 1, don't change anything to the column, and you keep doing it until you step out of bounds. That's going up. +1 and 0 is going down. 0 and +1 is going right. 0 and -1 is going left. And then this is -1 and +1. This is +1 and +1, and so on. -1 and, no, sorry. This is +1 and -1, and this is -1 and -1. Okay, you can do this. You can try to make it into a loop so that you have 8 directions to look through 8 directions, and you use these as what we call delta R and delta C to decide which direction to look. So you don't have to write the same thing 8 times. You just write a loop that loops through the 8 directions and then scan it forward whichever way. Okay, so all of that you can probably figure out how to do eventually. Maybe if this is the first time you do it, maybe it takes a little bit longer. But I want to show you a completely different way of doing it. In fact, I'm not even going to store the grid. So let's first start by checking if 2 queens are in the same row. That means that they are attacking each other. So what I'm going to do is that I'm going to say that there are 8 rows, 0, 1, 2. There are 8 rows, 0 to 7. And whenever I see, so I'm going to loop through I'm going to just read the input, right? The inputs is R and C from 0 to 7, 0 to 7. And whenever I see a queen, I remember what row I'm in. So this is row 2, let's say. And I would increment this number. At the beginning, they're all zeros. Every time I see another queen, I would increment this number. At the end, what should I see? At the end, I should see that they are all ones. There should be 1 on every row. If any one row is missing, that means you don't have 8 queens. And if any rows have more than 1, that means that row has 2 queens that can kill each other. Okay, so I just need a single dimensional array, and I can just, as I go through, figure out if I see two queens in the same row. And if I do, then I can say it's no good. Same thing with columns. I can do the same thing, right? I can check the columns and make sure that each column has exactly one queen. All right. Now here's the part that maybe will be a little bit of a unusual thing for you to think about. What about diagonals? Okay, so let's look at this diagonal. How many diagonals are there? There are actually 15 diagonals. So diagonals, let's call this diagonal 1. So diagonal 1, there are actually 15 of them. Why are there 15? 0 to 14. It starts, let's say, from here, then here, then here, all the way to here, but also goes this way. And if you count, basically, there is one starting at each spot on the top or on the bottom, not on the left. And this spot is doubled up, so it's not 16 different ones, but 15 diagonals. So I want to be able to figure out if two queens are the same diagonal. And one of the things that when you look at the coordinates, let's say on this diagonal, 2, 0, row 2, column 0, row 3, column 1, row 4, column 2, and so on, you realize that in this diagonal, the row minus column index, it's always 2. In fact, if you look down any diagonal, the row minus column index is always the same. Or in other words, if you take the row and column of a certain spot and you subtract it, that will give you a number that uniquely identifies the diagonal. And here's 7, 0. 7 minus 0 would be 7. Here's 0, 7. 0 minus 7 would be minus 7. So the diagonals actually go up from minus 7 all the way to 7, 15 of them. We don't like negative numbers in my array index. So what I'm going to do is, instead of saying just take row minus column, I'm going to take row minus column plus 7. And that will put me to 0 to 14. So what am I going to do? As I'm reading these queens, not only am I going to mark which row and which column they're on, I can figure out which diagonal they are on by taking the row and column of the queen, compute R minus C plus 7, and whatever that gives me, I increment that spot by 1. And again, if I ever see a spot that has more than 1, that means I have 2 queens on that diagonal. That's no good. Now, in this case, it's possible for some diagonals of zeros, because I have 15 diagonals, I only have 8 queens. I cannot fill them all. So some diagonals are zeros. You just want to make sure that none of the diagonals have more than 1. Okay, what about the other diagonals? So diagonal 2, if you go the other way, so this way, again, there are 15 of them. And this time, for example, let's say this is 4, 0, or 0, 4. The next one would be 1, 3, 2, 2, and so on. And you realize that this time, R plus C, it's constant along the diagonal. And R plus C is always between 0 and 14, because the smallest they can be is zeros, and the biggest they can be is 7 plus 7, which is 14. So you take the coordinates of a queen, add the rows and column, and that will tell you which diagonal you're on. And again, we can use this array like this, make sure that no diagonal has more than 1. Some diagonal can have 0. And that would be an easy check. So why is this any better? Perhaps you can say, why is it any better? And the reason is that you don't have to scan along the lines to find your queens, which saves you an extra loop of 8 iterations. You might say 8 iterations is not much of a big deal, but if you have a bigger board or if you have other problems where you need to look up diagonals or lines, then maybe if the board is bigger for other problems, then this saves you an order n. Okay, so it'll be faster by a factor of n. In this case, just 8. Okay, so that's kind of what I want to show you, and I want to show you my code now. All right. So again, I have the diagonals that I talked about. Actually, I guess what I call diagonal 1 when I just talked about here. In the code, I call diagonal 2. I got the 2 diagonal switch in my explanation, but more or less the same thing. If you just make that switch mentally. So I, at the beginning, set them all to zeros. I have not seen any queens. Then I'm just going to read. Actually, I don't even know why I have this line. Probably I copy and paste from the last program and then I didn't erase it. Okay, so anyway, I read with the double loop, 8 by 8, read 1 character at a time. If it's an empty space, I can ignore it. If it's not so if it's a dot, that means it's an empty square, I can ignore it. Otherwise it must be a queen. So I mark the row, mark the column. Oops, hang on. Let me just make sure you can see it. Okay, so I have these arrays that initialize the zeros for the rows and columns and diagonals, total number of queens. Then I check 8 by 8, read 1 character at a time. If the characters is empty, if the dots, that means it's not a queen, so I can ignore. So I skip the rest of the loop. Otherwise, I mark the row and column. I mark the first diagonal with R plus C, mark the second diagonal with R minus C plus 7. I remember that 1 more queens. And that's it. Now I got to check everything. So what do I check? First, I have a Boolean variable good that checks if it's still good and make sure that, first of all, I have 8 queens. If I don't have 8 queens, I'm done. Then for each row and column, I check that the row and column value is exactly 1. There's exactly 1 queen on that. This, oops. Okay, I guess, yeah, I got some short interruption here. Let me see, share screen again. Okay, so here, for each row and column, I check that row I and column I are both 1. And then I use this and equals that basically says, take whatever was there before, whether it's true or false, and this one, and if they're both true, then assign it to true. So basically, this allows me to combine whatever value I had before and with the new value. And then the diagonals, I check the 15 diagonals that they're both at most 1. And if after I check all the things, it's still good, I print valid, otherwise I print invalid. Okay, so this is a technique that I want to show you. The last problem is called numbers on a tree. And if you read this problem, it has this labeling that's sort of backwards from the bottom to the right and so on. And you're given the height of the tree, etc., and then a path. So I actually don't know easily how to get this numbering, but I did it backwards. Because we know that if you learn about binary heaps, usually we number things this way. Okay, so 1 level at a time. from left to right, and so on. Okay. This is exactly backwards of what they want. Okay, exactly backwards. So what we can do actually is that, do you know that in a height 3 trees, they're exactly 15. Why? Because this is 2 to the 3 plus 1 minus 1, which is 15 nodes. And it turns out that the answer that you want is actually 15 minus 14, 15 minus 13, 15 minus 12, and so on, right? Because if you look here, it's basically backwards to the number that we have. So 15 minus 14, 15 minus 13, and so on. And 15 minus 0 is 15. So actually, all we need to do is to do the numbering that we're familiar with for binary heap, and then subtract from it the number of nodes, basically the number of nodes from the tree. So that is what we're going to do. We can figure out the total that we need. This is the total. And then we're going to figure out the numbering with the normal binary heap. How does it work? Roots is 0. And whatever node you are in, left child, it's always 2i plus 1. And right child, it's always 2i plus 2. So what you do is, for example, if the sequence I give you is RLR, you start from the root, which is 0. Go to the right, you take 0, multiply by 2 plus 2, you come here. Left, 2 times 2 plus 1, it's 5. Right again, 2 times 5 plus 2 is 12. So all you have to do is walk down this string and either go 2 times I plus 1 or 2 times I plus 2. So the most important thing is to recognize, I guess, that this is the backwards of a standard binary heap, and then make use of that. So I'll just show you my code. So here it is. I read in the height and the string. I start with the node being 0, that's the root. For each string, for each character in the string, left or right, I always make 2 times the node plus 1. And if it's the right, then I add 1 more, because it's always 2 times node plus 1 or 2 times node plus 2. So I just go 2 times node plus 1, and if it happens to be the right one, I add 1 more. And then at the end, I just take this. So this is 2 raised to the power of h plus 1 minus 1. Generally, if you want to say 2 to the some power, 2 to, I don't know, n, then you can take the number 1 and left shift n times. That would be your, why is that? Right, so if you take the binary number 1, left shift n step, that's like adding n zeros to the right of it, and that's equivalent to multiply by 2n times. It's the same as decimal, right? If you have 1 and you want to multiply by 10 squared, what do? You put 2 zeros, and that's multiplied by 10 squared. So in binary, it's the same thing, except instead of multiplied by power of 10, you multiply by power of 2. And when you do bit shift, you have to be a little bit careful about the brackets, because the shift operator has some strange precedence rule that you might not be used to. So instead of bothering to look it up every time, I always just bracket everything just in case. So this is 2 to the h plus 1 minus 1. And then, of course, I subtract the index from the normal binary heap. And that's the answer that I get. So these problems that I chose, for the most part, they're not too difficult, I hope. They don't require a lot of algorithmic thinking, but that little tricks here and there that can help you write your code a little bit more concise and better. All right, so I guess that's the end of today. And on Wednesday, I'll post another set. See you later.